So let's talk about energy diagrams. Much simpler, but basically when we draw these graphs. So here's an energy diagram. This is energy versus the x direction. Okay, this is not a real thing because obviously a spring looks like a parabola and gravity looks like a linear thing. This is a random distribution of energy. Okay, so just a general case. So this represents the potential energy. Okay, if this is a closed system, what should total energy look like? A straight line, right? Because remember, total energy is constant. So at any point, the potential energy and the kinetic energy have to add up to total energy. And that means the total energy looks like this, okay? Where is this thing going the fastest? Where's the maximum speed? Yeah, here. Why is that? Right. The potential energy is like under this curve, right? The kinetic energy is above the curve. So this is the maximum kinetic energy because it's the place where there's the most kinetic energy. Okay. So that's going to be our max speed. Where does this thing turn around? Like, for instance, can your object be up here? No, why not? Yeah, you can't have more energy than your total energy. So everything up here is inaccessible, okay? And we would call these things turning points, okay? What does that look like in real life? This would be the no, you can't go there zone. All right, what does that look like in real life? Well, if you draw the potential energy graph for gravity, it just looks like a line, okay? If I throw this thing up, depending on how much energy I give it when I throw it, that sets the total energy. So you can move this line up and down. If I throw it harder, the line would be higher up. If I throw it softer, the line would be lower down. And that initial external force, that work that you do and where you give the system energy, that limits how far you can go along the graph. This is just a general potential energy for the system, but what you can get to in that potential energy depends on how much initial energy is put into the system, okay? And this will make more sense when we talk about stuff that's more familiar. We'll actually look at these graphs for the things that we do, but this is the general idea. Also, if you think about this from a calculus perspective, any relative minimums and maximums are called either stable equilibriums, meaning stuff like this, and then this would be an unstable equilibrium. So any valleys are stable equilibria. This would be, obviously your maximum speed, but you would have like another space here, because anytime you have a curvature like this, that represents like a restoring force. Okay, so for instance, for a spring, you have a parabola. That means if you pull the spring this way, it wants to go back to this, which would be the equilibrium point. Okay, so we'll talk about that in terms of springs. But yeah, these are unstable and stable equilibria. So from a calculus perspective, all the relative maxes and mins are going to be equilibrium points. Okay, and I mean, if you really just want to look at this as a hill, like if this is topography, if you put something in a valley, it's a stable equilibrium, right? So if you put something in the bottom of a bowl, if you pull it up the side of the bowl and let it go, it's going to just end up back in the bottom of the bowl. If you put something on top of a hill, it'll stay there, but if you tap it in either direction, it's going to roll down the hill. So that's an unstable equilibrium. It'll stay in that point unless you tap it. If it's in a stable equilibrium and you tap it, it'll try to go back to that point. Okay, cool. So let's talk about gravitational potential energy. What does that look like? What's the potential energy graph look like? Linear, so it looks like this, okay? If we draw our total energy, what should it look like? Different, the same? Still the same, right? It's a constant. So let's find the things on here. Where's the maximum speed on this graph? That's the maximum potential energy. So if this is a ball, right, you could start it here because this doesn't depend on time. This is the maximum height, right? As it drops, it's going to go down like this. So down here, what's the potential energy?
0.
So the kinetic energy is at its max down here. So this is the So this is your potential energy. This is your kinetic energy. Maximum kinetic energy is here. So this is your max speed. This is our turning point. Remember, you can't go higher than this because of our total energy is limiting where we can go. And what happens here? Well, you could start here, right? Where this would be all kinetic energy. So you could throw it up. That would be the point where it turns around. That's what we call it, a turning point. Okay. So if this is this point and I throw it, the top of the arc is this point. So if you wanted to track what's happening to the ball, if I'm throwing it up, it goes like this. Okay. If I drop it, it just goes like this. So this, where you are on this graph is not linear in time. Okay. But it does depend on your height and your speed. Cool. So here's this including a potential energy bar graph. Okay. So here at this point, right, if you launch something up, the kinetic energy is all of the energy. All right, so that's the fastest speed. At this point where it's traveling upwards, it's slowing down. So kinetic energy goes down, but it's higher up. So potential energy goes up. Okay. And if you add this plus this together, it should be the same as this because the total energy is the same. Okay. Once you get up here, you're at your peak, right? No kinetic energy because that's the turning point, meaning the velocity is going to be 0. But there's total potential energy, which should be equal to this plus this, which should be equal to this. Okay. And yeah, and as it turns around, you get back to this middle state. For the spring potential energy, what does that look like? It's a parabola. Okay, what does the total energy look like? Straight line. Where is our max speed here? At the bottom, right? So the bottom should be the maximum kinetic energy. This is where it's going the fastest. On a spring, right? This would be the stretched, this would be compressed, this would be the equilibrium length. All right. Our turning points, what are those? Well, if you pull the spring out, that's its maximum displacement. And then if you let it go, it'll squish in and there'll be a turning point there and it'll go back and forth. So it'll be stuck between those 2 points, which are dictated by the initial amount of energy you put into the system. Okay, which is your total energy. So here are our turning points. And what this looks like is basically the same thing, right? When you're all the way stretched, that means you only have potential energy. As you're going in, you have less potential energy and more kinetic energy. Right at the middle, you have all kinetic energy, then you switch again. Okay, so same general idea. All right, do we feel like we understand this? Do we have any questions about it? Let's find out. So it's A or D. Please discuss. We'll vote again. Oh, what's the D? Good job, guys. So let's talk about this. Actually, I'm going to draw on this. Okay, looking at this, what is this graph missing that the other graphs had? The total energy line, right? So how do we figure out what the total energy is? Yeah, so we let's see, we'll do that with red, I guess. So it tells us, right, it has 1 joule of kinetic energy at x equals 1 meter. So x equals 1 meter is here. All right. So that means the total energy is going to be potential energy. What's the potential energy? 3, right? Plus kinetic energy. How much kinetic energy do we have? 1. So that means we can draw our total energy line. Oh man, if I were better at drawing, that would be helpful. Let's make it thicker. Oh, too thick. Okay, so that's our total energy line. We know it's always 4 joules because this is a conservation of energy situation. So we want to know, where is the particle's turning point? Well, that's where those 2 lines cross. So the particle's turning point has to be here. And where is that on the graph? Well, that's at 6 meters. Okay, so that's going to be D, which is 6 meters. Does that make sense?
Yeah.
Yeah. So at every point, right, things have to add up. So at 2 meters, how much kinetic energy do we have? 4 joules. How much potential energy do we have? 0. At 4 meters, how much kinetic energy do we have? How much potential energy do we have? 2. Yeah, so at each point, potential energy plus kinetic energy just has to add to 4. Okay.